You're gonna be for dynamics, you can take any other math class because those two combined, it's already. That's like what you're gonna use.
Okay, number 3. Let's do it.
Oh, I see.
When I say let's do it, I mean let's all do it together, please. So the velocity is a function of the x component of the position. So we have velocity as a function of x is equal to x squared 2x cubed. Okay, so we don't have the velocity as a function of time. So we're trying to calculate the acceleration vector. We would like to just be able to take the derivative with respect to time, but we can't. Okay, so we got to use the chain rule. So the acceleration is the derivative of the velocity with respect to x times dx dt. And so that's the derivative of the velocity vector with respect to x times the x component of the velocity. And so dv dx is 2x for the x component, 6x squared for the y component. Now, what's the x component of the velocity? Well, we have the x and y components of velocity right here in front of us. So now I'm going to multiply this by x squared. And so you get 2x cubed 6x to the fourth. And that's the acceleration as a function of x. Yes?
Are we allowed to divide the x and the y component by x squared?
Are we allowed to divide, you mean as a way to simplify the answer? Or?
Yeah, is this a vector that we're able to deliberately get one in either our x or our y component?
Say that again. I don't think I follow.
I think it's eigenvectors that we're able to simplify it where you either have one in your x or y component.
Oh, no, these are, no, because, so you can do that with eigenvectors because every linear multiple of an eigenvector is also an eigenvector. This is actually, this magnitude is important.
Okay.
Yeah. Yes?
Since we have different values for every component, whether it's x, y, and z, how do we get in the future? I mean, if I'm getting too ahead, how do we get the value of acceleration like as a whole?
Oh, like as a single number? I mean, this is it. I mean, and so like if you want to know what the acceleration vector is at x equals 4, then just plug 4 in there and that tells you the acceleration vector, So this just gives it to you as a function of x. You know it at every location. Yeah. Any other questions about that one? I think 6 is probably similar, right? So let's do 6. Oh, no, it's not.
4 and 5 are the same thing.
4 and 5 are the same thing. But you want to see 6, right? Someone wanted to see 6. Okay, so this one, we have the velocity as a function of time. So that's good. It means all we have to do is solve separation of variables to figure out the position or take the time derivative to figure out the acceleration. And I think this is asking for both. So for part A, what's the particle's acceleration as a function of time? that's the easy direction. You don't have to use any boundary conditions. So acceleration is d dt of the velocity. And so that's derivative of the x component here with respect to time is 5. Y component with respect to time is -1. And so there you go. That's the acceleration as a function of time. Which, I mean, since there's no time in there, it's just components, that says that this is a constant acceleration vector all through time, you know. And now for B, this is the slightly more complicated direction. So what we have is, so we're trying to find the position, and I'm going to rewrite the velocity by the definition, you know, dx dt is equal to 5t, and dy dt is equal to -t. For the x equation, the boundary condition we have says that x, when time is equal to 0, is equal to 1. And for the y, it says x, when time is equal to 0, is equal to 1. Okay, so we have two separate differential equations, and we just have to solve both of those. So for the first one, dx is equal to 5t dt. And so x is equal to 5/2 t squared plus our first constant. Now we'll use the boundary condition for x, and it says that x is equal to 1 if you set t equal to 0. So C1 is equal to 1. And so now I'll update my best knowledge up to this point for what x is, and x as a function of t is 5/2 t squared plus 1. Any questions about that one? And now we'll go to the second one. So it says dy is equal to -t dt, right? Yes. Integrate both sides. I'll pull the negative out. Let me write the integral here. And so this says y is equal to -t squared over 2 plus some new constant of integration. And now we'll use the boundary condition. And that says that y is equal to 1 when you set t equal to 0. So C2 is also equal to 1. And now update. And you get that y as a function of time is equal to -t squared over 2 plus 1. And then if you wanted to write these together, you could think of this as the position vector as a function of time is equal to, for the x component, 5/2 t squared plus 1. For the y component, -t squared over 2 plus 1. And there you go. Anybody have any questions about that one?
Just scroll up. Thanks.
Yeah. Okay. Any other homework questions that you'd like to see? All right. So now we're going back to, going back to the chain rule. And so we're working on cases where the velocity is known as a function of a position variable. So the problems you've done so far have been cases where you're given the velocity as a function of x, y, or z, okay, where that's the starting point. But you can also use this approach in cases where you're given the path that an object travels along, like say by a function, like say this particle is traveling along the path. I think the example I gave last time was like cosine of x. So it's traveling along that path. And let's say we either know that it's going to the left or the right, okay? You can use the chain rule for problems like that. Well, you also need to have an expression for the speed. But the way you do stuff like that is we first have to figure out a unit vector that at any x value or, any value of that position variable gives you the direction that the particle is moving at that instant. Okay, so let me do another example. Let's just sort of break this whole process down into two different things. So let's say we have a particle that we know is moving in this way. Let's say we have sort of like an expanding helix. Okay, and the coordinate system I'm going to use is x, y, z. Okay, and so let's say that this, so if you parameterize this function, you would represent this as like z times cosine of z, z times sine of z, and then z. Okay, so this is a parameterization. This is like, you can think of this as the position as a function of z. Does that make sense? Can you make sense out of that parameterization? Like think about, basically like at any z value, what we have is this thing is going in a circle. Because if you have a vector like, let's say cosine of x, sine of x, then what this is doing as x increases is just following the unit circle around. Can you see that? Mm-hmm. Okay, so that's the idea of what this is. We have the third component that says it's also rising as it does this, so that's what makes it a helix. Are you with me on that? And we also are multiplying by z, so that's the thing that as z gets bigger, this helix is getting a bigger radius as you go.
The z component is just z because it's going up.
Yeah, right. And this is, notice that, so with these you always have to think, is this thing moving in the direction of increasing or decreasing value of the parameter, okay? Our parameter that everything is defined by is z. I've drawn the arrow this way, so this is moving in the direction of increasing parameter z. Okay, and what we want to do is, let's say we first want to find a unit vector in the direction of motion for any value of z. Okay, then we want to use that to find the velocity as a function of z. Then once we have the velocity as a function of z, then we're at that point where we can use that chain rule approach. So at that point, we want to find the acceleration as a function of z using the chain rule. One thing I haven't given you here yet is a speed for this. You always have to have some representation of the speed. Let's just go with a constant speed. Okay, so we'll say that the speed always is 5 meters per second. Okay. Anybody have any questions about what we're trying to do? Okay, so how are we going to find that unit vector in the direction of motion? Well, remember that once you have a parameterization like this of the object's location, if you take derivatives of all the components with respect to the parameter, it gives you a vector, not a unit vector, but just some random length vector that's always tangent to the path in the direction of the parameter increasing. Okay? So the first thing I'm going to do is I'm going to find this vector. So I'm going to find this vector that's not a unit vector, not unit length yet. And I'm just going to call it u. And that's tangent to the path in the direction of increasing parameter. So u is, so if this is a parameterization of the position vector, u is d dz of this parameterization. So, and let me say, this u always is going to be plus or minus. I'll mention that in a second. So plus or minus. What's the derivative of this position vector with respect of the x component of the position vector with respect to z?
What was the question?
What's the derivative of the x component of p with respect to z?
Minus z sine z.
Okay.
Time plus.
Yeah, so we got minus z sine z, yep, plus
cosine of z.
Perfect, yep. And then for y, we're going to do a similar thing. We have z cosine z plus sine z. And then what's the derivative of the z component with respect to z?
1.
1, yep. And now we have to think about the plus or minus. So the way I have this problem drawn is this object moving in the direction of z increasing or decreasing? Increasing, so we want this. If I had drawn that picture moving down where z was decreasing, I would have to multiply everything by -1. It would be the opposite of what I have here. Okay, are you with me on that? I know this is a little confusing, but okay, so we have I'll just rewrite this. So we have negative z sine z plus cosine z. For the y component, we have z cosine z plus sine z. For the z component, we have 1. Now, at every instant, at every z value, this is in the direction of motion of the particle. Okay? That's what's cool about this. But it's not a unit vector yet. And we need it to be a unit vector because we want to be able to multiply it by the speed and have it represent the velocity vector. Okay? So right now, like say at some z value, let's say the magnitude of this is 1.6. Well, if you multiply 1.6 by 5, you don't have something with a speed of 5. So we first have to get it as a unit vector so that when we multiply it by the speed, it's a velocity vector. Okay? You can always get a velocity vector by multiplying a speed times a unit vector in the direction of motion. Any other questions right now? Okay, so how do we get this as a unit vector? We have to divide by the magnitude. The magnitude is, so we have negative z sine z plus cosine z squared plus z cosine z plus sine z squared plus 1 squared, all square root. I'm not going to spend a lot of time simplifying this, but this actually might simplify a little bit. There's one important trig identity that can be helpful in this case when you have sines and cosines. So let's see, what do we have? If we, did you guys learn FOIL or did you call it something else?
FOIL.
Okay, thought kids today learn everything so different. Okay, but FOIL this out, you know. So you got z squared sine squared of z minus 2z sine z cosine z plus cosine squared z plus,
How is it called in English?
what?
Is that how is it called in English?
Is what?
How is that technique called in English?
In English? Yeah, yeah, you're just distributing this, you know, square. But to us, we learned FOIL, first, outside, inside, last. So that's what, I just call it foiling. So now, now I'm squaring out the second term. So we have z squared cosine squared z plus, I'm running out of room, 2z sine z cosine z plus sine squared z plus 1. And it's the square root of all this. And now I guess you can choose which one you want to use the one with. Notice that so let's use the more complicated one. Maybe that'll help us simplify this a little bit. So I'm going to group this and this and this. Nope, we can't do that. So we just have to do it with the cosine squared, the sine squared, and the 1. Okay, so cosine squared of z plus sine squared of z is equal to 1. So this is equal to 2 plus z squared sine squared of z plus z squared cosine squared of z.
That's just z squared, right?
What?
Is that just z squared?
That's a z squared, yeah. Oh, this thing, yes, you're right, yes. And then look at these two guys canceling.
Oh,
And, okay, now we're getting somewhere. So this is u magnitude is equal to 2 plus z squared. That's cool. That worked out great. And so now that we have that magnitude, we can finally calculate the unit vector. That is the full vector divided by the magnitude.
Quick question, how
Yeah.
did you go again from the top to the bottom? The z plus, or 2 plus z squared?
Oh yeah, well,
Or was it just cancel?
sine squared of
Okay, yeah.
anything plus cosine squared of the same thing is equal to 1. Okay, so now we'll go back up to this, and we have 1 over the square root of 2 plus z squared times our vector negative z sine z plus cosine of z, z cosine of z plus sine of z, 1. And that's it. So at any z value, this is a unit vector in the direction that the object is moving. Okay? So now the velocity vector is just equal to the speed times this unit vector. So I guess I'll write this as, so I'll write this as 5 times negative z sine z plus cosine z, and then divided by this, I'll write that as 2 plus z squared to the negative 1/2, just to set it up for easy derivatives. The y component is 5 times the quantity z cosine z plus sine z times the quantity 2 plus z squared to the negative 1/2. And the z component is 5 times the quantity 2 plus z squared to the negative 1/2. And that is the velocity at any instant as a function of z. Yep.
I'm going to do a bad job explaining this question. Is the position vector, the derivative of that velocity, a vector pointing towards its current position, or is it something else?
The position vector? The position vector is going from the origin of the coordinate system to the particle at any z value. But it's not the derivative, it's the other direction. But yes. So this is the position vector, and based on that position vector and this speed, we can calculate that this is the velocity at any z. And now for part, oh, that was B, I guess. A was hard, B was easy. And now what about C? Now we want to know the acceleration. Why do we keep wanting to know the acceleration so bad? Like, why don't we just be happy with the position and the velocity? There's a question for you.
Force.
Yes, exactly. So right now we're in kinematics world, but there's only one way that you can go from particle kinematics world to particle force world, and that's through Newton's second law. And Newton's second law has acceleration in it. That's why acceleration is so important to us. Okay? So if all you care about is the kinematics, then you're probably happy with the velocity and the position. But if you're trying to go into figuring out the force now, you gotta re-express, you have to figure out the acceleration to do that. Okay, so now C. I'm sort of waffling on whether we're actually going to compute this derivative. I mean, look how ugly it is, But all I want to point out is, and these always get ugly because you're dividing by a magnitude, So unless things really, really simplify a lot, it's going to be an ugly derivative. But notice that now all we have to do is, now we're at the point where our previous chain rule problem started. We have the velocity as a function of a position variable, and that means that the acceleration is just equal to dv dz times dz dt. And that means dv dz times 5, let me put this in brackets, times the quantity 2 plus z squared to the negative 1/2. Because that's the dz dt is the z component of the velocity vector. And so just look at the velocity vector and just take what's in the z position and multiply it. Okay, as far as this thing goes, you kids love emojis, I know.
Discuss it on tests, right?
Yeah, right. Right. Well, actually, on tests, we have a 50-minute class. I don't want you spending the whole time doing derivatives. So on tests, like if I ask a question like this, it's usually one or the other or two separate problems. Like either I give you the velocity as a function of a position vector and tell you to calculate acceleration, or I ask you to just come up with the velocity as a function of the position,
Wait, does that mean if we have only 1 hour of lecture, our exam would be only 2 questions and 50 points each?
Yeah, it's not 50 points each, I guess. I just don't score it that way. But yes, that's right. The tests will probably be 3 or 4 questions most of the time, Yep.
So why is going from position to velocity so much more involved? Is it because we explicitly set a magnitude that velocity is equal to?
Then going from
Velocity to acceleration, so same direction, but the next step is easier. So.
Oh, well, I guess it's just like what that velocity is made out of. That velocity is made out of this unit vector. And to get that unit vector, you have to do 2 things. You have to take a derivative, which can make things messy. And then you have to divide by the magnitude, which is the thing that makes it really messy, and then multiply by the speed. So it's just the steps, And actually conceptually, this is easy, going to the acceleration, but it's going to get brutally more ugly when you take this derivative. This is actually the step where it's going to get the ugliest.
Oh, yeah.
Okay, let's do another one. Okay, so let's say we have this object moving along the function. So let's say y is equal to negative 2x squared. So what does that look like if this is the coordinate system? It looks something like this, and let's say that it's going this direction. And so this is just going to be a two-dimensional problem. There's no z to worry about. And we want to calculate the acceleration vector of this particle as a function of x, given that its speed is, let's make it constant again. Let's make the speed 4. Okay, well, the first thing we have to do is come up with a parameterization from this function. So how would you represent this as a position vector? This is how it always works if you're given functions, if you're given it as a function like this. Well, the position vector is xy, right? That's the definition of x and y. And that y, we're told, is equal to negative x squared. So this is just x negative 2x squared. So that's your parameterization. If you, no, it does not, you cannot show the direction it's moving in that parameterization. All this is giving you is a relationship between one point and the x value and the y value. And so the way that that negative x direction is going to come in is when we're choosing the direction of that vector. That's when that plus minus here is going to, we're going to take the minus here. Yep. Okay, everyone feel good about where we are here? Okay, so now the first thing we're going to do is find a vector, not a unit vector, but some unknown length vector in the direction of motion. And we're going to do that as, so this is plus or minus derivative with respect to the parameter of p. And so that's 1 for the x component and negative 4x cubed for the y component. And this time we want the negative because we're going in the direction of decreasing x. Yep.
Is the derivative not just negative 4x?
Stupid. Yes, thank you. I took my derivative wrong. Okay, so now multiply both of these by, think of multiplying this vector by negative 1, and you just get negative 1 positive 4x. So that's a vector with an unknown length, but in the direction of motion. Everyone with me on that?
Yes, sir.
Yay. And so now the magnitude of this is 1 squared plus 16x squared square root. So 1 plus 16x squared square root. And so now our unit vector in the direction of motion is just this vector u divided by the magnitude. So you can think of that as negative quantity 1 plus 16x squared to the negative 1/2. And for the y component, this is 4x times the quantity 1 plus 16x squared to the minus 1/2. And now we want the velocity as a function of x. And so we're just multiplying this unit vector by the speed. So the velocity as a function of x is, the speed was 4, so multiply both of these by 4, you get negative 4 times the quantity 1 plus 16x squared to the negative 1/2. And then in the y component, 16x times the quantity 1 plus 16x squared to the negative 1/2. So for this object that's moving with a speed of 4 meters per second along this path, at any x value, this tells you the velocity vector. Okay? Like at any x value, if you plug in x equals -1, you get a vector that's tangent to the path in the direction of motion, and its magnitude is the speed. Okay, so now how do we get the acceleration? The acceleration is dv dx times dx dt. So this is dv dx times dx dt is the x component of this velocity. So we're multiplying it by, let me give that a bracket, -4 times the quantity 1 plus 16x squared to the power -1/2. This thing is a mess. It always is. But it wouldn't be so horrible to do that, you know. Well, we're out of time. Otherwise, I would do it right now. But
Convenient.
but I mean, obviously, you could plug that into Wolfram Alpha and do it. You know, some of your calculators will do it. So,
Bring a laptop to tests.
yeah. Well, like I said, on tests, I really never make you struggle through those derivatives. I mean, you already took a class where you were graded on how well you did derivatives, so I'm not going to be another class like that. But really, this is just about understanding the steps of how this works. And, you know, you can make your intern calculate that derivative for you. Okay, any questions?
No?
Okay, that's all.
Oh, yeah.
Goodbye.
How many hours today?
Office hours, no. My office hours are Tuesdays and Thursdays from noon to 2, and Fridays from 11 to noon.